All right, so here we are, and you guys are studying next year for step 1, and you're paging through your notes and you're doing your board review, and you're looking through all the pathology. You're going through pathoma, you're going through first aid, and you hit the section where the basic science comes up, physiology, and you think, oh yeah, I got to study this stuff too. Got to know something about it, you'd hope. So you're paging through your course notes, or you're reading material. And you hit this, and you go, okay, that makes sense. Frank Starling, increased preload, increased stroke volume, increased cardiac output. I got that down. They beat that into my head like a pulp, okay? So you got that down. Makes sense. Increased stretch, increased stroke volume, increased cardiac output. Now you're paging along, you're going a little bit farther in the course notes, and you hit this thing. And you go, wait a second. Wait a second. Way back here, it says cardiac output goes up, central venous pressure goes up, cardiac output goes up. Direct relationship. This one says cardiac output goes up, central venous pressure falls. Inverse relationship. What is going on? You know, what was Dr. Shannon breathing when he put this thing together? Okay? Because whatever it was not pure air, right? Because this is exactly the opposite. It can't work this way, right? Wrong. It actually does work this way. Both of these curves are true, okay? I know it's confusing, and I know it's a pain, and I'm sorry about that. I didn't make it up. I just lecture on it, okay? Here's what happens. Your x-axis has your independent variable, your y-axis has your dependent variable. This is what you change, and this is what you measure. So if I set up a heart and I isolate it, and I have blood or something flowing into the right atrium here, and I have a pacemaker and I measure the cardiac output here. If I change the pressure, the venous pressure, by changing the height of this reservoir, I increase the central venous pressure, I increase filling, and if I measure the cardiac output and the stroke volume, it goes up. And it looks like this relationship. Now, if I take the same setup, but I keep the height the same, which means I keep the central venous pressure the same, and I alter the cardiac output with a pacemaker, what I get is, as the cardiac output goes up, the central venous pressure falls, okay? So if you vary the cardiac output, your central venous pressure falls. If you vary the central venous pressure, your cardiac output. If your central venous pressure falls, your cardiac output falls, okay? So both relationships are true. It depends on what you're changing. If you're changing cardiac output, central venous pressure changes. If you're changing central venous pressure, cardiac output changes. Okay, that tells you how it works in isolation. How does it work in real life? In real life, what you do is you take your Starling curve, where you have cardiac output or stroke volume here, and this is what it looks like. As I increase central venous pressure, I get an increase in output. And what you do is you flip the vascular function curve so that now, instead of the CVPs on the y-axis, you put it on the left and you put cardiac output on the right, and now you've graphed them both on the same graph. Where the system operates is the point where these two curves intersect. It's called, not surprisingly, the operating point or the equilibrium point. Okay? So if you want to know how the two things operate together, increased cardiac output, fall in CVP, decreased cardiac output, what you get is the operating point right here. That's where everything comes to steady state. Now we give a blood transfusion, and I said if you increase the blood volume, you get a parallel shift in the vascular function curve. So now you've increased the central venous pressure by adding blood to the system, okay? And you've shifted your vascular function curve. Well, that means that you're now getting an increased central venous pressure because you've added a lot of blood to the venous system, okay? And that means that your cardiac output goes up, right? Because I've added blood, I've increased central venous pressure, I've increased filling, I've increased stroke volume, cardiac output goes up. You see that here. Cardiac output goes up, what happens to central venous pressure? Falls. And what happens is you end up at the new point of intersection. Okay? Now, I am not concerned that you know all the little backflips and mental permutations I did to get to that point. I am concerned that you know that the new intersection point is the new operating point, and that you are operating at a slightly higher central venous pressure, maybe not as high as you might have thought it should be, but a higher central venous pressure and a higher cardiac output when you give a blood transfusion. That's the operating point. Okay? So, if you like the arrows, this is how you get there. You increase the central venous pressure with the transfusion, that increases cardiac output. That makes your central venous pressure drop back again toward the original value. You don't get back to the original value, and you end up at the new operating point. And what I really want you to know is where they intersect. Okay? Okay.